Every second of every day, millions of gallons of raw municipal wastewater surge through subterranean infrastructure, demanding immediate mechanical and biological intervention. For decades, the objective was simple disposal. Today, modern frameworks like the Enforce model outline a highly optimized circular system. The goal is to transform these processing sites from municipal liabilities into what engineers call resource recovery plants. The targeted commodities in these plants are highly specific. Operators aim to extract phosphorus by precipitating a mineral called struvite, capture biogas to generate grid electricity, and process agricultural biosolids to replace chemical fertilizers. The concept is mathematically and environmentally elegant. The reality is that wastewater engineering is governed by the rigid techno-economics of sludge dewatering, the costly physical process of separating heavy solids from water. To understand the economics of this separation, we have to measure the input. The industry standard is the population equivalent, or PE. It standardizes the average daily organic waste load produced by a single person. This map visualizes the 2021 Ireland wastewater dataset, mapping facility locations by their PE capacity. The data reveals extreme variance across the national infrastructure network. At one end of the spectrum, rural facilities operate at an almost microscopic scale of just 50 PE. At the opposite extreme, massive urban hubs like the Ringsend plant in Dublin operate at a capacity of 2.2 million PE. Before any biogas can be captured or struvite precipitated, engineers at every facility, regardless of size, must confront the mass balance of dry solids. Dry solids, or DS, refers to the actual mass of the waste material when 100% of the water has been removed. The cost to isolate those solids requires specialized capital expenditure, or CapEx. And the data shows that this machinery scales non-linearly. The cost per user heavily favors massive populations and severely penalizes small towns. The physical toll of managing raw water mass dictates the financials. A circular resource economy requires paying that biological and mechanical entry fee first. We can calculate exactly what that entry fee looks like by examining the unit economics of a centralized, mid to large tier facility processing 150,000 P. The standard biological treatment process produces secondary activated sludge. Engineering baselines establish that this process generates exactly 30 grams of dry solids per P every single day. Multiply those 30 grams by 150,000 people over a year, and this facility generates 1.64 million kilograms of secondary activated sludge annually. But those solids do not exist in a vacuum. They are suspended in water. At this stage in the treatment process, the physical output operates at only a 1% solid concentration. This 3D model represents the true spatial reality of that 1% concentration. To manage those 1.64 million kilograms of solids, the plant must handle 163,432 cubic meters of total material per year. If a municipality attempts to transport or dispose of this material, 99% of the logistics budget is spent moving heavy, completely useless water. To stabilize the budget, aggressive volume reduction is required. Water must be forcibly extracted. The minimum viable target is 20% dry solids. Hitting that threshold shrinks the volume from over 160,000 cubic meters down to just 8,171. Going from a 1 to 20% concentration is unnatural. It requires extreme mechanical intervention to break the bonds between water and waste. Mastering the physics of that volume reduction is the mandatory bottleneck. A plant's ability to finance this specific mechanical step dictates whether it faces operational bankruptcy or breaks even. Reaching 20% density requires heavy industrial machinery. Plants rely on mechanical belt filter presses and high-speed decanter centrifuges to physically rip water from the sludge. This table shows capital trade-offs for a 150,000 PE plant. The Alpha Laval centrifuge demands 330,000 euros in capex, but OPEX is relentless. Power costs 21,600 euros annually. Achieving 20% solids also requires injecting synthetic coagulants. These polymer costs add a massive 65,700 yearly penalty. Why do engineers and municipalities tolerate these massive energy and chemical OPEX penalties? We have to calculate the alternative. Disposing of the wet, untreated 1% sludge costs approximately €90 per physical ton in transport and spreading fees. Dewatering the sludge to 20% solids mathematically offsets the machinery cost. By dropping the total transport and disposal volume by 95%, the plant avoids millions of euros in logistical penalties. These brutal mechanical and chemical costs are not optional upgrades. They are the fixed operational entry fee required before advanced resource recovery can be considered. Applying this math to a decentralized rural plant reveals a severe structural barrier. Let's analyze a small municipality operating at just 500 PE. The physical output here is fractionally small. A 500 PE plant produces only 5,475 kilograms of dry solids over an entire year, 1/300th of an industrial centrifuge. This chart compares the CapEx efficiency between the two plants. There is an absolute capital floor for mechanical dewatering, which severely inflates the cost per kilogram at the smaller facility. For the 500 PE site, a basic belt thickener and press combination still requires an upfront capital investment of €152,000. The mandatory chemical infrastructure does not disappear at the scale either. Installing the required polymer mixing and pumping systems adds another €68,000 just to achieve baseline functionality. The resulting scale penalty is extreme. The capital cost required to process a single kilogram of solids is exponentially higher for decentralized plants than for urban hubs. Because the 500 PE plant produces so little waste, its €220,000 dewatering system only runs 12 hours a week. By contrast, the 150,000 PE plant runs its machinery 108 hours a week. In project finance, this creates a stranded capital asset. The expensive machinery sits idle for 156 hours a week, physically depreciating without generating continuous operational value. The strict physics of sludge mathematically punish small-scale operations. Implementing advanced resource recovery technology at this decentralized level is financially unsustainable. This brings us back to the enforced business model and the pursuit of a fully circular wastewater economy. This theoretical balance sheet visualizes the proposed revenue streams. Biogas sales, avoided emissions penalties, and the commercialization of fertilizer are supposed to generate enough capital to offset the baseline operational costs. But capturing those resources requires installing anaerobic digesters, or struvite precipitation reactors. This adds millions in additional capex on top of the already intensive dewatering baseline. When we connect this model to the 2021 dataset for Ireland, the market reality becomes clear. Outside of the basic agricultural spreading of treated sludge, true multi-resource recovery is exceptionally rare. Most plants simply do not have the user base to justify the capital expense. The singular exceptions in the data are massive centralized hubs, like Cork Harbour or the Ringsend facility in Dublin, shown here. Operating at a capacity of 2.2 million PE, Ringsend produces enough centralized volume to justify advanced infrastructure. The facility utilizes anaerobic digestion to capture grid energy and refines its treated sludge into highly specific horticultural byproducts. The financial mechanism that allows Ringsend to achieve circularity is pure scale. Their immense capital expenditure is aggressively amortized across millions of daily users, driving the unit cost of recovery down to a viable margin. The circular resource model is technically flawless, but only when a facility operates at a scale massive enough to absorb the severe upfront mechanical penalties of water extraction. The transition to a circular wastewater economy is not gated by chemistry or environmental policy. It is strictly governed by the uncompromising techno-economic boundaries of sludge mass balance.